Okay, so I've already put out 3 videos on how to go about calculating the distance of the Earth to the Moon. The first one was an introduction to this particular series, along with the first method I thought of where the ancient Greeks could have calculated the sun's diameter in degrees. Now what we need to do is we need to estimate how big the moon is. Now, unfortunately, we can't really do that with a measuring tape, and there is no direct correlation between the size of the sun and the size of the moon. We need to find a different way, and the easiest way to do that is by looking at the stars. Now, I recorded this backwards, but I'm going to manually scrub the video backwards so that you can kind of get an idea. So keep an eye on this star right here. And you can see that as time goes on, you can also see the time over here. So as I move the time this way, you can see that at 3:19 a.m., that star has just lined up with this edge of the moon. So 3:19. Now, if I keep going a little bit further, you'll see that it's just going to start popping out from the other side at 4:14. So 3:19 to 4:14, it's taken 55 minutes for the moon to go in this direction. So I've done a few of them and I've aggregated it, and they are somewhere around a minute and an hour and 9 minutes. So let's say that the average is an hour and 9 minutes. Before I get on to the purpose of this set of videos, which was to calculate the distance of the moon from the Earth, I need to cover and make sure that it's clear in people's minds what a penumbra and an umbra is. So I drew a diagram of the sun here, and I drew the blue ball here is the Earth, and this one I made black. I could have made it gray, but I made it black. The black lines represent the light that emanates from each of these 2 points of the sun. We've got this surface of the sun that emanates light in this direction. And if it goes on this side of the Earth, the ray of light continues to go in this direction. The one on the bottom that goes in this direction will go on the other side of the Earth, and it'll cast a shadow that goes like this here. So that basically creates a triangle that you see in black here, being in complete shadow of the Earth, that there is no light coming from the sun in this particular region. Now the other regions, the light will kind of continue to come off in this direction over here and partially illuminate this side over here. And same thing with this. So there's going to be a point where this side will go on this side and it'll illuminate this area here that's in gray. So really the only point that is completely obscured by the sun is what you see in black. What you see in gray is partially illuminated by the sun based on those angles. And I drew the red lines here for the moon. And you can see I made the moon a little bit smaller, and the umbra is not quite as long here. This is not quite as long as this here. So that's basically the first part of what I'm trying to get across here. And particularly the second part is going to be how do we go about calculating the distance from the Earth to the Moon. And this is basic straight trigonometry. Now I'm going to show how I arrived at this number here. This is going to be 2.75 moon diameters. So if the moon is here and it's in line with the Earth, these angles will represent the same 0.5 degree umbra cone caused by the sun. So the angles will be the same. The only difference is that because this one is much smaller than this, you can see it's actually 3.75 times smaller than the size of the Earth, that you can see its shadow only extends as far as the moon's orbit. So it's just something that you really need to be clear in your mind how this works. It took me a few minutes of really head scratching just to get it right as to how these ratios work. But in essence, the moon umbra is at a 5-degree angle. So this angle here is 5 degrees. If this is 5 degrees for the moon's umbra, this would also be 5 degrees for the Earth's umbra, because the sun is over here on this side. The ratio of this object's diameter to its length is going to be the same ratio as this object's diameter to this length, which is going to be the same as this diameter to this length. So the ratio is going to be the same on all of them. So in the end, the way that we calculate the distance from the Earth to the Moon is to estimate how many moons are required to equate the Earth's diameter. In this case, it's going to be 3.75. I think it's 3.76. So once we get 3.76 Earth's moon's diameters to represent the Earth's diameter, then we can calculate this distance here by dividing this length by this number, which will equal this, and thus it will give us this. Now we get to the meat of this particular set of videos. How do we go about measuring the distance of the Earth to the Moon? So if you look at the Moon as it traverses the shadow of the Earth so that you get a lunar eclipse, you can clearly see when the parts are red, that is behind the Earth's umbra. When it's silver or partially cast silver, then you know that it's in the penumbra. And you can clearly see when it starts to go into the penumbra because the moon starts to get dim. So the first thing that the ancient Greeks could easily have done was to just look at the moon, and they'd be able to see when it started to go behind the Earth. We've already established how fast the moon travels one moon diameter. Let's take a look at this. So this is a view of the moon as seen from the Earth, where the black part is the umbra and the gray part here is the penumbra, and of course the white is where the sun is not obstructed by the Earth or by the moon. And when the moon just enters the umbra, so that when the trailing edge of the moon just lines up with the one side of the umbra, from that point to the point where the leading edge just meets the point where the umbra and the penumbra meet, that is the eclipse totality. So keep these pictures in mind as we will be going on in a little bit. So the greatest eclipse occurred on July 2000, lasting 106 minutes. That is where the moon went right through the center of the Earth's shadow. We need to add the time that it takes the moon to traverse its distance to get the total travel time. When this edge just lines up with this edge, that's when the clock starts. And because it's going in this direction, it will continue to go until it reaches something like this, where the leading edge is now just touching the border between the umbra and the penumbra. So that is the total travel time. But it may not necessarily be a full moon diameter. This is just a measure of time. So what we need to do is we need to add 1 moon diameter travel as well, so that we can get this time from this edge to this edge, so that the moon is now no longer in the umbra at all. So what we do is we add this one particular moon transit time. So let's take 106 minutes and divide that by 60. So that took 1.76 hours in July 2000. Let's just give an average of an hour and 2 minutes. So now what we need to do is we need to add 103 to this. So we got 2.7999 moon diameters. Sorry, no, that's 2.799 hours. So that's 2.799 hours for the moon to go from here to here. Of course, now we divide by the amount of time that it takes the moon to go 1 diameter. So if we divide that by 1.0333333, we get 2.7096. Let's just go 2.71. Okay, so we now have 2.71 moon diameters. So going back to the trigonometry that I showed earlier, we take the Earth's diameter, which is 6371 kilometers radius, multiply that by 2, and then we multiply that by 0.55 tangent inverse equals 1.327 million kilometers umbra. And then if we divide that by 3.71 moons, we get 357,775 kilometers distance to the moon, and the real value is 384,400 kilometers. And somebody can plug the different numbers into the equations and get different numbers, but when I was doing this, I got anywhere between 500,000 kilometers to 300,000 kilometers. And that is how the ancient Greeks could have calculated the distance of the Earth to the moon.